Chapter 6.1 is finding the area between curves now, not just one curve, but between multiple curves. So let's go back to some of the basics here. For example, when we plot a point like 2, 5, what does that really mean in terms of distance? It means the distance to get to this point from the x-axis, from the y-axis is 2, from the x-axis is 5, right? Simple enough. If we have a function like y equals f of x, and we want to get to a point on the curve, we know that we go over an x amount, and depending on that x amount, we go up a y amount. And that distance from the axis to the curve is y. And from this axis to the curve, the horizontal distance would be x. Now, distance between 2 points works the exact same way, where I go from the origin, I go over 2. This might be 2, -3. I go over 2, and from the axis I go up 5. From the axis I go down 3, right? So the total distance here will become my 5 minus the -3, right? And if it was a +3, the distance would still be 5 minus the +3, right? So that subtracting automatically takes care of any kind of negative values that might be involved. So it won't matter whether my point is above or below the axis. Same thing goes for curves. If I have some curve y1 is equal to f of x, and then I have a lower curve y2 is equal to f of x, the distance between, the vertical distance between these two curves, right, will be to go from, I went over x and I went up a distance of y1 corresponding to this curve. And then I went over x and moved down to y2 corresponding to this curve. Now the distance is going to be y1, the upper curve, minus the lower curve. y1, it's a y value, don't forget, it'll be a y value, y1 minus the y2. So let's take a look at what that looks like in terms of an example. In this case, we have y equals, find the area between y equals x squared, this curve, and this curve. First of all, you should be able to graph these without a graphing calculator. You have a regular parabola that goes through the origin, which is not very accurate here, but looks something like that. That's pretty good. And then we have another parabola. This time, I can factor out the x. I get 2 minus x. I know that my x-intercepts, it's a sad parabola. It's an x-intercept 0 and 2. So 0 and 2, something like this is what I'll know. Now I want the area in this region. We know how to find exact areas, right? And the way that we do that is adding up an infinite number of rectangle areas. So we are going to split this into really, really skinny little rectangles. Now the area of a rectangle is going to be base times height. So we want the infinite sum of rectangle areas, base times height. Now don't forget the infinite sum, or the limit. It's a Riemann sum, but the limit as that sum goes to infinity, we've now figured out it is the definite integral. So we're going to find an infinite sum of base times height. Now what is the base of these rectangles? It's going to be my delta x, which will become dx. So this is the base, and I want to multiply it by the height of the rectangle here. Now that height is what we were talking about. The height will become the upper y value. So this from the x-axis up to this green curve is y1. So they will call this y1. And then the distance from the x-axis to this curve will become y2. So this rectangle height will become y1 minus y2. y1 minus your y2. Now that will become the height of these rectangles. So base dx times height y1 minus y2. Now we want to take the infinite sum of these only from this point to this point, right? We're not constantly cutting rectangles further than that. So what we want to do is find these points where this curve is equal to this curve, so we can set these two alike, because we are still looking for x values, don't forget. So we can set these two equal to each other. X squared equals 2x minus x squared. Solve, solve, solve. You'll see that x is equal to 0 and 1. So from 0 to 1, we're taking the integral of base times height. Now if I simplify this, x here, we want everything in terms of x. So from 0 to 1, I'm going to replace y1 in terms of x, and y1 is equal to 2x minus x squared minus your y2 in terms of x, which is just x squared. So take the integral of that with respect to x, work, 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 solve, solve, solve. You should get an area of 1/3. Let's take a look at the next example. The next example says find the region bounded by the curves y equals sine x, which starts at the origin, of course, goes down something like this. I might have erased something. And y equals cosine x, which starts up here at 1 and starts going down. But it also needs to be bounded here by x equals 0 and x equals pi over 2. So it has to cross the x-axis at 0, so it's a vertical line here, and x equals pi over 2. Well, right here where they're equal is pi over 4, right? Pi over 2 is going to be up here where sine peaks. It's a little crooked. This is going to be pi over 2. So the area that we want is going to be bounded by these two curves and these vertical boundaries here. So it's going to be this area as well as this area. Now, if that's the case, what do you notice about the rectangles that are being cut? Base times height. Base will be dx, but the heights will switch. The height for this very first region will be the upper cosine x minus the lower sine x. However, when we pass pi over 4, it'll switch for the upper boundary being sine x to the lower boundary being cosine x. So we have to split it into two integrals. So this will go from 0 to pi over 4 of the upper boundary cosine x minus the lower boundary sine x. That's the height of my rectangle times the base of my rectangle, dx. And then I have to add it to this region's rectangles, because it switches, right? So the height of this rectangle will become sine x, the upper boundary, minus cosine x, dx, from the region pi over 4 to pi over 2. Now what would have happened if I didn't switch it? Okay, so this is the correct method, and you should get an area of 2 square root of 2 minus 2, I think it was. Yeah. Now what happens if we didn't switch these boundaries and we did it all in one? So if this, for example, is all that we did, and we made this instead pi over 4, then this boundary, the area of these rectangles, would be the lower boundary minus the upper boundary, which would give me a negative value. And because these two regions happen to be symmetrical, this would have yielded an area of 0, which we know is not true and would be incorrect. So be careful of those. Make sure that when you draw your rectangles, they are continuous. They are the same height all the way across. Taking a look at our last example shows us a very good example of checking. So, if you have the area of the region bounded by y equals x minus 1 and y squared equals 2x plus 6. So I've already drawn the picture for you, and it looks something like this. So if we cut a rectangle going this way, the base of my rectangle will be dx. It's an infinitely small change of x. The height of my rectangle will be this green curve minus the purple curve. This curve minus this curve. However, if I were to draw the rectangle, move the rectangle over this way, notice what would happen. The height of the rectangle is a green curve minus the green curve, which will yield 0. So that doesn't give us anything. It doesn't actually tell us anything when we know that there is a most definite area here. So it obviously, from this point on, it gives us kind of a problem. There's an issue here, right, on this left-hand side. But there's nothing that says that we have to cut our rectangles vertically. So what we're going to do instead is we're going to cut our rectangles horizontally, this way. Now then, if you notice, if I run my rectangle all the way up and down, right, which fell apart, but if I run my rectangle all the way up and down, or if you tilt your head sideways, this purple curve will always be above the green curve. The purple curve will always be greater because it's more on the positive side than this green curve, which is more on the negative side. So now what this integral would look like. Now we know that one of the dimensions of the rectangle is dy, right? It's delta y, infinitely small, so it's dy. So this is, I guess, from this angle it'll be the height, but that's one dimension. Now I want to multiply it by the other dimension, and that's going to be from the y-axis this way to this curve is going to be an x sub 1. So the purple will be x sub 1, right? Remember, to get to a point on the curve, to move horizontally is an x value. And then to move horizontally from the axis down to a point on this curve will be x sub 2 over here. So what that's going to give me, in order to get the other dimension of this rectangle, I'm going to have to do x1 minus x sub 2. Okay. Now, we do want it in terms of y, though. We do want it in terms of y, which means these boundaries better also be y values. So these boundaries, I am actually looking for these y values. This is my A. Oh, sorry, this is my A, the lower boundary, and this is my B. So we want those to be y values, so we're going to solve those by setting the two x's equal to each other. When you set the two x's equal to each other, you'll find that A is equal to -2 here, and the upper boundary B is equal to 4 here. Now the only thing left to do, y equals -2 to 4. The only thing left to do is to convert these x values back to y. So we need to solve for x sub 1, which is y plus 1, right? Minus, we need to solve for x sub 2. So x sub 2 is going to equal to y squared minus 6 all over 2. Like that. Okay, so in one integral, all we have is a polynomial. You can solve for the area between these two curves this way. You'll find that if you do the work to get 18. So be careful of which way you want to cut your rectangles.